of this school plus small workshop. So our first speaker in the evening session is Pritam Chattopadhyay from ISI Kolkata, and he will tell us about thermal engine from uncertainty relation standpoint. Pritam, please go ahead. Yeah. Okay, great. We can see your screen, and your cursor is, I think, also visible.
Okay. So it's working, right? Means the screen
yes,
slides are working, right?
Yes, absolutely.
Okay. So can I start?
Yes, please. Please start. Yeah.
First of all, I would like to thank the organizer for organizing such a wonderful summer school event and allowing me to be a part of this one event. I'm Pritam Chattopadhyay. I'm a student of Indian Statistical Institute, right, working under the supervision of Professor Gautam Pal. His work was done jointly with Gautam Pal and Mitra and Bachelor Zerisco. Today, I'm going to talk about this thermal engines from the uncertainty relation standpoint, which happens to be a part of this paper which got recently accepted in entropy under the title Found on Efficiency of Engine from Uncertainty Relation Viewpoint. It was studied in the non-relativistic regime. This work was further extended to the relativistic regime, where we have studied the relativistic quantum heat engines from uncertainty relation standpoint. This paper got accepted at scientific report. Before moving into the details of the talk, let me give a brief outline about my today's talk. I will give a brief outline about the domain of the research, that is the thermodynamics. Then we will move into the motivation of the work, and then I will say about the results that we have obtained during this analysis of this work. And finally, I will conclude my talk with its concluding statements. So first of all, what is thermodynamics? Thermodynamics is a predominant area of physics which deals with the connection between heat and work and the transformation from one to another. The development of the thermodynamics can be divided into three phases. In the first phase, which we describe here as the thermodynamic first wave, started from the work which was given by Carnot, where he developed a Carnot steam engine, which helped France to win the Napoleon War. This gave birth to the thermodynamics. Next, we can say that the development of thermodynamics came from the work which was given by Joule, where he designed a water friction apparatus. He proved that energy cannot be created nor be destroyed, but can only change its form. This idea is known as the conservation of energy. This experiment consists of a brass paddle wheel, which is used to store water in a copper vessel. Now, Kelvin came into this field and showed that Carnot work was foolproof, and then he extended and said that thermometry are not used to obtain absolute temperature because they are used for calculated temperature, and designed a new scale which is known as a Kelvin scale for the measurement of temperature. Next, a big contribution came from Clausius in the year 1854, where he proposed the statement of thermodynamics second law. We will go through this laws of thermodynamics in the next coming slides. The second wave, that which we say as the microscopic descriptions and the development of statistical mechanics, came from the work of Maxwell's and Boltzmann and Gibbs, where Maxwell first, with the help of Boltzmann, designed the Maxwell-Boltzmann distribution. It is a result of the kinetic theory of gas. The distributions was derived, surfaced on the fact that it will maximize the entropy of the system. Boltzmann in 1857 designed the Boltzmann equation, which is popularly known as Boltzmann-Planck equation. Is a probabilistic equation which relates the entropy of the system with the number of microstates corresponding to the system's macrostate. This was what was extended by Gibbs in the next year, that is in 1876, where he generalized the work of Boltzmann's equation by defining the entropy for the arbitrary ensembles. Now, thermodynamics has a wide field of application, starting from the analysis of thermal engines, refrigerators, which happens to be one of the primary focus of thermodynamics. Along with that, climate changes and chemical reactions are also analyzed with the help of thermodynamics. Even it is considered that thermodynamics can unreveal the properties of the black hole and unfold the hidden mysteries of our universe. With the paradigm shift in 20th century, where we see that microscopic world has been changed. The analysis of the microscopic world has shifted to the microscopic world. As classical physics was unable to explain various physical phenomena like black body radiation, quantum scattering, and so on. Due to this, we have one question pops up in on the researcher's mind, whether we can see the existence of thermodynamics and the resilience power of thermodynamics even in the quantum world or not. To understand this, researchers started to explore thermodynamics in the quantum regime, and this is popularly known as the quantum thermodynamics, which happens to be the third wave of exploration of thermodynamics, which we popularly now study as quantum thermodynamics. We see that there is a resilience power of thermodynamics to every theory of physics, because thermodynamics use the said world, that's a present world, very efficiently, and every theory has to abide by the laws of thermodynamics and comes to thermodynamics for its advice. Now let us explore the thermodynamic laws in classical regime first, then we will go to the quantum regime. In classical regime, Zeroth Law states about the thermal equilibrium of the systems. Let us consider three systems here, A, B, and C. So if A and B are in thermal equilibrium and B and C are in thermal equilibrium, then we can say that A and C is also in thermal equilibrium. So it's the Zeroth Law describes that we have thermal equilibrium as an equivalence class, and temperature levels the difference between this equivalence class. The first law of thermodynamics conveys about the energy conservation principle, where the change in the internal energy is shown by this equation, du equals to dq plus dw, where du is a change in the internal energy, which is equals to the sum of the change in the heat and change in the work. Now the second law of thermodynamics. There are various versions of second law of thermodynamics. The first statement was proposed by Clausius, where he has stated that heat will not flow spontaneously from a cold body to a hot body without an external work on the system. In other words, we can say that the entropy of the system will be same or will increase with the rate of change of time. Now, let us study the laws of thermodynamics, the quantum world. In quantum world, first of all, we see various different features which are not present in classical world. So the Zeroth Law, as mentioned in recently, that it conveys the thermal equilibrium as an equivalence class where temperature is the only parameter. But in quantum realm, we are not going to have the thermal equilibrium in such a way, because we will encounter various quantum phenomena in the quantum world. Generally, in thermodynamic process, we consider the system and the environment is uncorrelated. But during the execution of the process, it can happen that the system gets correlated. If we consider the system and the bath are correlated, then we encounter a violation of the equilibrium principle. So a generalized Zeroth Law was coined, which conveys that we can infer mutual thermal equilibrium for a set of states only when no work is extractable from any combination of the states under the entropy preserving operation. To satisfy this condition, all the states have to be in thermal states with same temperatures. Now, the first law of thermodynamics in quantum world can be analyzed by considering a system with finite number of energy levels. The change in the internal energy is defined in this form, where Pn describes the occupation number and N is the energy levels the system. If we equate this one with the previous classical equation, then we see that dW is equals to En, this first term of the equation, and the second term describes the change in the work. Now, as based on the various approaches, second law has been defined in various ways. Here we have considered that one of the definitions which is considered is that the the working system is not correlated with the environment, which is described in this initial state, rho initial state, which can be defined as the tensor product of the system as well as the environment. So the change in the entropy is always positive if we consider the system to be uncorrelated. This is one of the form of the second laws. There are various other forms based on applications. Now, with the advent of quantum thermodynamics, we see that various aspects of quantum thermodynamics are under studies, like resource theory, thermalization, quantum thermal machines, fluctuations, and so on. In this talk, we will be concentrating on quantum thermal machine for our analysis. For the analysis of quantum thermal machines with that is like quantum thermodynamic cycles, we consider various quantum systems for our analysis purpose, like particle in a potential well, harmonic oscillator, spin-half particles, and so on. We will be considering particle in a potential well as a working medium in this work. And we have also analyzed harmonic oscillator for our work in various other works, which like where we have considered a non-commutative space structure, that is a defined space structure for where we have considered this harmonic oscillator as a working medium and have analyzed the efficiency of the engines, and have encountered that the non-commutative parameter provides a boost to the system, boost to the system as well as efficiency of the working mediums and the efficiency of the engine. So first of all, what is heat engine or heat machine? Heat machine is a device which converts heat into work. The first, as I already said, that first Carnot engine, first engine was proposed by Carnot, and it's named under him as the Carnot engine. It's a 4-stroke engine consisting of 2 isothermal and 2 isentropic steps. Carnot engine is has an efficiency which is known as the Carnot efficiency, as happens to be the highest efficiency for any engine when acted upon 2 heat baths. It is mathematically defined as work output by heat input. In other form, we can say that 1 minus TL by TH, where TL is the temperature of the cold bath and TH is the temperature of the hot bath. There are further examples like Otto cycle, which is used for the analysis of Otto engines, which consist of 2 isobaric and 2 isentropic states. We have Stirling cycles, which are used for the analysis of Stirling engines, which consist of 2 isobaric and 2 isothermal states. For our present talk, we will be using this quantum Stirling cycle for our analysis with working medium as the potential well. With the shift of paradigm from the macroscopic world to the microscopic world, analysis of the thermal engines in this domain have got significance. These are some of the seminal papers where we encounter the signatures, quantum signatures in thermal engines. Stirling in their work have shown that the presence of coherence in the quantum state of the systems will enhance the work output. Even we can improve over the Carnot limit. Also, Kostov's group have shown that if we have coherence, we can generate more power in the quantum engines than that of the classical stochastic thermal engines. Now, if we change the bath from a normal bath to a squeezed thermal bath, then we can see the efficiency of the Otto engine can exceed the Carnot efficiency. These are the few works that have been done in the studied in this domain. Along with that, we encounter entanglement has enhanced the performance of quantum refrigerators, which is solely a quantum phenomenon. So now let us understand quantum Stirling cycle with potential well as a working medium. The representation of the total cycle has been shown in the left-hand side of the figure. Left-hand side of the slides, we can see that T1 is the temperature of the hot bath, T2 is the temperature of the cold bath. The phases are depicted in by 1, 2, 3, and 4. In the first phase, we insert a partition which divides a potential well into a double potential well when the system is connected to the hot bath. This is done isothermally. Along with that, we take care that the tunneling probability tends to 0, so that there is no tunneling in between this process, and the thermal process time is much more. Thermal process time is much less than that of the tunneling time. The second phase of the cycle, the system is connected to the cold bath, where the heat is released. This is done is an isophoric process. The third phase of the cycle, the system is connected back. We remove the partition isothermally and convert the double potential well into a second potential well when the system remains connected to the cold bath temperature T2. This is also an isothermal process. And the final phase of the cycle, we revert back the system to its initial state where the system was connected to the hot bath at temperature T1. So heat is added in this process. So now what is the motivation of this work. The primary motivation was to study the Stirling cycle with infinite potential will as a working medium from uncertainty viewpoint. Second, we thought of to develop a bridge between the thermodynamic systems with the uncertainty relation of these incompatible observables of the working medium. That is the position and the momentum of the particle in the working medium. That is the potential will. And the final point was to analyze the useful work without executing any measurement, but by using two reservoirs as of two different temperatures. So, first of all, I will understand what is uncertainty relation of a potential well. This is a well-known textbook problem of quantum mechanics. So I'm not going into the details of this one. The wave function of the potential well or the system is defined as shown in equation 3, where 2L is the dimension of the potential well. So having the wave function in our hand, we can develop the eigenvalues of the potential well, which is defined as n square pi square a square squared by 2m, 12 square, where m happens to the mass of the particle. Having these ingredients, that is a wave function and eigenvalues in our hand, we can develop the uncertainty relation of this model, which is defined in this form as shown in equation 4a. Now, having developed this uncertainty relation, we will move to understand the uncertainty relation that we have developed for our analysis. We have developed the thermal uncertainty relation for our model, which is defined in equation 5, where n bar is described as root over pi alpha beta, where beta is the inverse of temperature and the constant Kb is the Boltzmann constant, and alpha is of the factor pi square h square by 2m 2l square. For our analysis, we will be using sum of uncertainty relation for our for the fact that the product uncertainty relation will not be able to capture the uncertainty of the incompatible observables when the wave function of any of the observable happens to be the eigenfunction of one of the observables. Why? If we consider this Heisenberg form, then there is no problem. But in recent times, we have seen that many works have been done to improve the lower bound of the uncertainty relations, which was provided by Heisenberg in the 1995. One of the recent papers, which was done by Mondol, and it was done under the supervision of Arun Kumar Pati, where they have shown that the lower bound of the uncertainty relation for the position and the momentum operator can be defined in this form, which gives a better lower bound than provided by the lower bound of Heisenberg uncertainty relation. While studying, we have encountered that if we take this form of our analysis, we encounter that the product uncertainty relation is unable to capture the uncertainty in the incompatible observables. So, for the better understanding, we have to use the sum uncertainty relation for our analysis. The reverse uncertainty relation, which is known as the upper bound of the system, is defined in this form, where COV A is the covariance, and there is a condition that this equation, this lower denominator lies between -1 to +1. The results of the reverse uncertainty relation for our model is of this structure, which is shown in the second part of the equation of 8. So this is a variation of the thermal uncertainty relation with a change of the length of the harmonic oscillator, where we have considered n is the n bar with the systems to be 1 and 2. We see that for higher values of n, this is the upper bound and the lower bound is getting closer. So we can expect that for higher values of n, the upper and the lower bound will merge together, and the area bounded by this one is more in case of n equals to 1, and area bounded by the two curves, that is upper bound and the lower bound, is quite less in n equals to 2. Now, this is a variation of the sum uncertainty relation with the length of the potential well for two different temperatures. We see that sum of uncertainty increases with the increase of the length, and this is quite obvious because with the increase of the length, we can see that sum of uncertainty increases because with the increase of the length, delta x increases and delta p decreases in case of Heisenberg uncertainty relation. But in our case, if we see that the first term of the equation 6 that contributes from the delta x, and the second term which comes from the contribution of the delta p, it has an exponential term. So with the increase of the length, we see an increase of the uncertainty relation over the momentum component. So having the uncertainty relation in our hand, Now, if we want to correlate the thermodynamic variables with the uncertainty relation, we have to bridge a connection between the thermodynamic variables with the uncertainty relation. So first of all, for that, we have to first of all analyze the partition function of the system with the uncertainty relation, which is described in equation 9. But Ct is some variable which is a function of length and temperature. Now, having the partition function in our hand, we can develop the Helmholtz free energy, entropy, and so on of the thermodynamic variables, where the entropy of the system is defined in equation 10, where gamma and nu are functions of alpha, beta, which are function of length and temperature of the system. So here we see the variation of the entropy with the sum of uncertainty relation. Here we see that entropy increases with the increase of sum of uncertainty relation, and this is quite obvious because as the chaosness of the system increases, we see that there is an increase in the entropy of the system. Now let us understand and develop the efficiency of the Stirling cycle with in the point of view of uncertainty relation. In the first phase of the cycle, where we insert the partition, the change in the heat that takes place is defined as UB minus UA plus KBT ln ZB, where ZB is the partition function of the system at at the position B, and ZA is a partition function at the position A, and UB is the internal energy when the system has when the partition has been inserted inside the L, and QA is the internal energy when the partition was not inserted inside the L. Now the QBC is is a change in the energy, a change in the heat when the system is connected to the colder bar. There is a release of heat during this process. So this is described by the change in the internal energy as UC minus UB. In the third phase of the cycle, we isothermally remove this partition and revert back the two double potential well into a single potential well. The change in the internal energy is defined as UD by UD minus UC, where UD is the internal energy of this well and UC is the internal energy of this well, where when there was a partition was inserted in the well, and when it was removed, then we said that the energy of the internal energy of the system as UD. And ZD is a partition function of this system and ZC is a partition function of this system. In the final phase, this is reverted back to its initial stage when it is connected to the temperature, hot bath at temperature T1. The change in the heat is defined as UA minus UD. So the efficiency of the system is defined as, the efficiency of the system is defined as 1 plus QBC plus QCD by QDA plus QAB, which in terms of the uncertainty relation in our model is defined in this structure, where D and E are function of the uncertainty relation at temperature T1 and T2. Now this is a variation of the efficiency of the engine with respect to the sum of uncertainty relation. Here we can see that the upper bound gets asymptotic, that gets fixed to certain values of the uncertainty relations, whereas the lower bound decreases rapidly, then it becomes asymptotic for higher values of some uncertainty relation. The conversion rate of the thermal machines will decreases with the increase in thermal energy, and after a certain point of it gets saturated for the higher values of uncertainty relation. So what we can conclude here that every quantum thermodynamic variables has a direct connection with an uncertainty relation. Like we see that entropy has a direct dependence on the uncertainty relation. Along with that, we were able to predict the efficiency as well as the total work of the engine without performing any measurement. And we were able to provide a bound for the efficiency of the thermal engine. This work was extended, as I already said, in the relativistic limit, where we have studied relativistic Stirling cycle for our analysis and consider relativistic potential well, where we have to take care of the Klein's paradox. And along with that, we were able to conclude that in relativistic domain also we have same relationship as the direct connection between the uncertainty relation and the thermodynamic variables, and we were also able to provide a bound of the efficiency for the thermal engines in the relativistic domain. So I would like to conclude my talk here.
Thank you, Pritam, for first of all for finishing very much in time and for the nice talk. So, okay, so we are open for questions. Please unmute yourself and ask. Any questions? questions? I have some questions. If nobody asks, then I will ask. But nobody has questions.
Let me share my screen.
Okay. So, Pritam sir, I have a quick question.
Yeah.
So, when you define efficiency, these are probably all the things which go into the calculation of efficiency are usually expectation values. These are expectation values of some operator. Is that correct?
You are asking this one?
Yeah, I mean, whatever is defined as an efficiency.
Yes.
Ultimately, when you look at it from the perspective of the quantum mechanical system, is it a collection of expectation values of some operators?
Yeah.
Maybe. Okay. So, which basically means that given each expectation value, there is a standard deviation around that expectation value.
Yes.
Probably related to the whatever uncertain relation.
Yes.
Now, how much is this? Is there an estimate in the whatever efficiency you're predicting, the expectation values which have gone in? How much is the fluctuation around it? Can one estimate that? How much, which is like how much is the error? See, imagine the situation where your averages are of the order of your fluctuation. Then, though the efficiency looks very nice, it might be completely meaningless.
Yes, I am getting your words. So regarding the fluctuations, we have not taken. We have not seen whether what is the percentage about that, about this around these values. But surely we will look into this and let you know about that one.
Okay, so this is something which one has noticed, because when one is saying that you're going beyond the Carnot limit, it might be very important to calculate. I think when Carnot engine's efficiency is being predicted, I think the assumption is there somewhere in the background the fluctuations are not crazy.
Yeah, but our one is bounded by the Carnot efficiency. This one is bounded by the Carnot efficiency.
Right. But even in the quantum limit, when people are talking about these exceeding, I'm just curious because you are also using a quantum device. How the fluctuations are going to influence your prediction.
I will look into that, but in case I think the fluctuations have to be taken care of. In this, we have assumed that that it is not affecting too much into the system because because we have considered the system gets to equilibrium because we are giving too much time for them to get into that equilibrium state.
I see.
So that using that one, we have rejected the components of that can come from the fluctuation.
I see. Okay.
Sorry, I have a small question.
Please, yeah, please.
I'm still not able to get the physical principle. So internal energy difference, I understand. Now this KT log Z, where that expression comes.
Which one? This one?
Your phase 1, phase 3, for example. So I'm not sure what is going on. Is it a classical thermal kind of calculation, or is it that partition function is computed quantum mechanically?
Yeah, partition function is calculated quantum mechanically, and the internal energy is calculated from the definition
of particle in a box.
Particle in a box. In a particle in a box. Yes.
Okay.
These forms are defined in classical form. We are using the working principle in the quantum domain, and using that we are calculating the partition function and the internal energy of the system.
Okay. But for example, are there any physical systems where these kind of things appear? Because particularly in a box, physically in many places it appears.
Yeah, in condensed matter, I've seen some papers that they are trying to develop potential well using some material designing, where they have used some material. I don't remember the material which they have used for the analysis, but they have used some materials using which they can design potential wells, and which can be further used for the analysis of thermal engines in their nanoscale domain.
So that is fine. This D and E, capital D and capital E, they keep track of the uncertainty.
Yeah, they keep track of the uncertainty, right?
Okay, I'll actually read it because it sounds interesting. You have paper in the archive?
Yeah, this is published in Entropy.
Okay, good. So I'll read it.
And along with that, this relativistic version is also published in scientific report.
Okay, very good. Very nice.
Okay, Pritam. So thank you very much for your talk, and we move on to the next speaker. So Nayana Das, Nayana, are you around?
Yeah, I am here.
Okay, great. So our next speaker is Nayana Das from ISI Kolkata, and I don't seem to have a title for her talk, so maybe she will tell us what her talk is about. Nayana, please go ahead.
Yeah. Is this visible? My
Yes,
screen?
it is visible. Yeah.
Okay. So I'm going to tell about two efficient measurement device independent quantum dialog protocols, which is a joint work with my supervisor Gautam Pal. And so first I'm telling about quantum secure direct communication. So in classical cryptography, sending a secret message always requires a key. For in classical cryptography, there are two types of schemes. One is symmetric key, and other one is asymmetric key crypto system. In symmetric key, there is a one shared key between two or more participants, which they use to communicate further. And in public key crypto system or asymmetric key crypto system, there are two keys. One is public key and one is private key, and both the keys are used to communicate. But in quantum scenario, QSTC can transmit secret message over a quantum channel without any key. So there are predefined encoding and decoding rules. Using that encoding and decoding rules, one can send a secret message securely without any key. So the first protocol of QSDC, secure model of the QSDC protocol was proposed by Deng and Long in 2003. They have used Bell states and Pauli unitary operators to send a secret message to Alice to Bob. The basic requirements of QSDC are the secret message should be read out directly by the legitimate users, and no additional classical information is needed to decode the message. And another one is the secret message should not leak even if may get hold the channel. So anyway, the secret message will be secure. Next, the quantum dialog is a process of two-way secure and simultaneous communication using a single channel. In 2004, Nagun first proposed the quantum dialog protocol, which is an improvement of ping pong protocol. Ping pong protocol is a QSTC protocol where Alice and two parties, Alice and Bobs, are there, and Alice prepares a bell states called Psi plus and send one particle from each bell state to Bob, who encode his message using Pauli unitary and send back to Alice. That is ping and pong. So that's why the name is ping pong protocol. And the first quantum dialog protocol is a improvement of this ping pong protocol. Then what is measurement device independent protocol? So in the measurement device independent scenario, all the measurements at the time of the execution of the protocol should be done by a untrusted third party who may be an Eve. So all the loopholes are eliminated in this protocol. Now we'll talk about the first NDI QD protocol proposed by Dr. Pritam Chattopadhyay, where Alice and Bob wants to communicate simultaneously. They first prepare a shared key using BB84 QKD and then prepare qubits corresponding to their message and the key. Then they send their qubit sequence to the UTP, and UTP measures the joint qubits in Bell basis and they declare the measurement results. And from the measurement results, Alice and Bob guess the message of each other. So the details of the protocol is Alice and Bob let's share the key stream K, which is given by this one, and then Alice's message is A. Then she prepares qubits corresponding to A and K. That is, the qubits are function of message bit and key bits and send it to UTP. Similarly, Bob also prepares QB and send it to UTP. Then UTP measures each QAI and QBI in Bell basis and announce the measurement results, which is a Bell state. So all the different cases are here. For the first 4 row, key bits are 0 and the last 4 rows, key bits are 1. So if the key bits are 0 for bit value 0, they will prepare qubit 0. For bit value 1, they will prepare qubit 1. And for if the qubit is 1, then they are prepared in X basis. So for 0, they prepare plus state, and for 1, they prepare minus state. So if UTP measures the joint states QAI and QBI in Bell basis, they will get the measurement results phi plus, phi minus, psi plus, psi minus with this probability distribution. Next, the decoding procedure. So from table 1, one can see that if Alice or Bob prepares 0 in Z basis, then if the measurement result is phi plus or phi minus, then the Alice's bits and Bob's bits are same. And similarly, if the results are psi plus or psi minus, then their bits are different. So here the cases are. So if the bits are same, then the measurement results should be phi plus or phi minus. And if the this first row and fourth row, and if their bits are different, then the second and third row, their measurement results should be psi plus or psi minus. Similarly, if they prepare in X basis, then if their measurements results are same, then the measurements results will be phi plus or psi plus. And if the bits are different, then the measurement results will be phi minus and psi minus. So they decodes the message bits using table, the previous table, and get the value of the other parties. So one can see that if the measurement results phi plus or psi minus, then let's first consider the measurement result phi plus. So phi plus is occurring when all the Alice and Bob's message bits are same. See the first row, fourth row, fifth and eighth row. So all the 4 cases, both the Alice's and Bob's message bits are same. Similarly, when psi minus occurs, Alice's bits and Bob's bits are always different. So if the measurement result is phi plus or psi minus, if always know the ZOR value of AI and BI, which is the information and causes information leakage. That's why Alice and Bob discussed those cases. That is almost half of the qubits. So we modify this MDI QD and propose two efficient MDI QD protocols. And we reduce the number of discarded qubits to half to almost 1/4. And our protocols are more efficient in qubit counts. So, and also we have showed that both our protocols are secure under the same adversarial model given in MDI QD protocol. And here is the reference of our paper. So our now we describe the first protocol. So first we calculate the ZOR value of all the key bits C. Then Alice and Bob's keeps all the MI, where MI belongs to phi minus or psi plus, that is as the previous MDI QD protocol. And among the remaining measurement results, they choose some of them to keep and discard the others. So how to choose? They choose phi plus or psi minus, and if Ki equal to C. And then they keep that measurement results, else they discard that. So the algorithm is, they generate a finite sequence xn such that xi equals to 1 when the measurement results are phi minus or psi plus, and otherwise the xi equal to 0. And they generate another sequence yn such that yi equal to 0 if xi equals to 1. That is, if mi equals to phi minus or psi plus, and yi equal to kj if c equal to 1 and xi is the jth zero of the sequence xn. Similarly, yi equal to kj bar if c equals to 0 and xi is the jth sequence of xn. Then for 1 less equals to I less equals to n, they will consider the ith measurement results mi if and only if xi zor yi equal to 1. So let us take an example for simplification. So if the key bit is this is a 20-bit key, and then the zor value is 0, that is c equals to 0, and let's Alice's message bits be this and Bob's message be this. Then using the encoding algorithm, Alice's qubits are this and Bob's qubits. Then they send QA and QB to UTP, who measures in bell basis and announce the results, and the measurement results is this. From the measurements results, and they generates the sequence X, that is when the measurement result is phi minus or psi plus, then they prepare, then the ith bit is 1. Otherwise, if phi plus, then the ith bit is 0. And for psi minus also, the bit is 0. They also prepare the Y sequence as described as before, and then calculate the zor value of x and y, x or y. So the zor value is this. Then they consider the message bits corresponding to the ones. That is, they will keep the first bit, the second bit, the fourth bit, like this. Then the Alice's message will be this, and Bob's message will be this. Now we describe the second protocol. Here also they will calculate the C value, that is the zor value of all the key bits, and then they keep the measurement results mi, where mi belongs to phi minus or psi plus. Among the remaining measurement results, they will choose some of them and discard the others. So the difference between the previous one and this one is the procedure of choosing the measurement results. In the previous protocol, they choose only ki equal to c, and here they choose the measurement results in two different processes for Alice's message and Bob's message. If mi equals to phi plus or psi minus and ki equals to c, then Alice and Bob keeps that mi for Alice's message. And for Bob's message, they keep the measurement results if ki equal to c bar. So the algorithm is, they generate the finite sequence xn as before, and another two finite sequence yn, z and zn. So yn is the same process as before, and zn is zi equals to 0 if xi equals to 1. That is the case where mi equals to phi minus or psi plus. Zi equals to kj, which is, this is the complement of this line. That is, zi equals to kj if c equals to 0 and xi is the jth 0 of the sequence xn. And zi equals to kj bar if ci equals to 1 and xi is the z0 of xn. And the decoding process is, for Alice's message, they will consider the measurement results if xi is or yi equals to 1 and the discards the other. And for Bob's message, they will consider the results if xi zor zi equals to 1 and discards the others. So we also take an example of the second protocol. So let us consider the key value is this. Then the zor of the key bits is 0. We also consider the message of Alice is BA and message of Bob BB. Then the Alice's encrypted message is this, like key bit is 1, so they will prepare in X basis, and message bit is 1, so they will prepare the Q bit minus. Similarly, key bit is 0, that means they prepares in Z basis, and message bit is 0, that is they will prepare 0. Similarly, they will prepare the other message bits, and Bob also used the same algorithm to prepare QB. Then they sends QA and QB to the untrusted third party who measures in the joint states QAI and QBI in Bell basis and announce the measurement results. And see, for the first one, the first state of QA is minus and the first state of QB is plus. So the measurement results is phi minus. Similarly, the others. And from the measurement results, they first create the sequence X sequence, that is phi minus means 1, psi plus means 1, phi plus means 0, psi minus means 0, psi minus means 0, phi minus means 1, that is like that. And the Y sequence or Z sequence are calculated from the X sequence and the key bits using the previous algorithm. Now the XOR value of X and Y is the sequence this, and the XOR value of X and Z is the sequence this. So they consider the Alice's message if this value is 1, that is the first, they will consider the first bit, second bit, they will discard the third bit, and like that. So they will consider this as Alice's message, that is the first, second, fourth, fifth, like that. And they consider Bob's message if X or Z is 1, that is the first bit, second bit, third bit, like that. And this is the final message of as Bob's message. So these two protocols we have proposed. And then we also generalize this MDI QD protocols to a quantum conference protocol. So what is quantum conference protocol is the process of simultaneously sending a message to multiple parties, that is for n equal to 3 or more. So we first generalize this MDI-QD to a 3-party quantum conference protocol where each party can send their secret message to the other 2 parties using the same procedure as described before. And then we propose a n-party QC. So for the 3-party QC, they have taken the help from 4th party, and for the n party QC protocol, they take the help from n plus 1th party, which may be an if. We also use the n party quantum conference protocol to propose a quantum n party XOR computation, which is a multiparty computation where the secret message of each participant will be secret, and they can get the XOR value of all the participants' secret message as a final output. So this work was published in QIC in this year, and I conclude my talk. And any questions? Thank you.
Hello.
Hello.
Somehow this thing got stuck. Yeah. Thanks for your talk. So any questions?
Yeah, I have a question. Either if
Okay.
there's nothing in chat box.
Yeah.
Nice talk, Nana. These things, what is the experimental status now? Has somebody tried this kind of protocol on IBM?
We have tried in QScript, so we are already implemented that.
Is it on simulator or is it on real?
Both. Also, we also simulate the protocols and then we ran it in IBM real devices.
Good.
Anybody else has any questions? If not, Naina, thanks again. And we move on to the next talk. Our next speaker is Dr. Aniket Patra. Aniket, are you there?
Yes.
Okay, great. And he's from Aarhus University, Denmark. And hi. And he will be telling us about driven dissipative dynamics of coupled atomic clocks.
Can I say a few words about Aniket?
Oh, absolutely, please.
It's a pleasure to see Aniket, such a pleasure. And Aniket was our second batch student. In fact, very deep memories are associated, with this because we all started our life together, and there are many incidents of, nice incidents here. I was associated with the hostel, and Aniket, of course, was a very good student. His notes were being widely followed and widely followed also.
Widely and widely. Okay, whatever that means.
Subsequently, he went to Rutgers. I distinctly remember this final year project presentations and things like that. He did his project with Professor Santol. And then, after I have kept track of his works also. And before, anyway, we will be having more occasion to discuss with him. Now he's back in Germany as a postdoc. So, sorry, I pass it on to you.
Thank you. Sure. Thanks for the interruption. Yeah, Aniket, please go ahead.
Okay, so I will now share the screen. Yeah.
Yeah.
Can you see my screen now?
Yes, I do.
Full screen. Okay, good. So can you see my cursor as well?
Yes.
So when I move it, yes?
Yes, absolutely.
Okay, good. So then shall I begin?
Yeah, please.
All right, okay. So thank you very much. First of all, I must thank Professor Panigrai, who taught us, when I was in ISI Kolkata, I attended many courses that he taught, first of all, and I again thank him profusely for inviting me to give a talk here, which is an absolute honor. And of course, it's it's really happy occasion for me to come back to my alma mater. So today I will be talking about this particular topic, which is driven dissipative dynamics of coupled atomic clocks. Now, this work was done at Rutgers University, whereas my current address right now is Aarhus University, which is at Denmark, and I'm doing my postdoc there. So let me begin with the talk. So the buzzword of this talk is going to be Z2 symmetry and chaotic synchronization. And I hope to explain the meaning of these two words at the end of this talk. So that's to keep in mind. Now, synchronization is a very old classical phenomena, first observed by Christian Huygens of optics fame. And so he essentially observed the opposite swings of pendulums of same length, permitting small experimental error, coincide when two pendulum clocks are hung from the same support. And this is an example of so-called anti-phase synchronization. And the reason was also identified by Huygens himself as the imperceptible motion of the beam. And this was the experimental setup that he saw the synchronization in. And this synchronization was also observed by J.W. Strutt, also known as Baron Rayleigh. And he said that when two organ pipes of same pitch stand side by side, is cause the pipes to speak in absolute unison in spite of inevitable small differences. Now, this is an example of so-called frequency locking. So these are like, two different types of synchronization, classical synchronization that was already known from a long time ago. Now, since this being the 21st century, we are in fact interested in quantum synchronization. What I mean by that is that we replace the classical clocks in the experiment of Huygens with atomic clocks. Now, first, let me explain what I mean by atomic clocks. So what I mean, first of all, is that we have an ensemble of ultra-cold two-level atoms, where the number of atoms is of the order of 10 to the 6, in a bad cavity. Now, the Hamiltonian is written as follows, where this S, these are the collective spin operators, and A denotes the cavity mode of this particular cavity. Then we add in incoherent pumping with rate W, and of course, the pumping is denoted by this Lindblad term, which is this Lindblad superoperator. And because this is a leaky or a bad cavity, we add in this other Lindblad term, which denotes the decay of that cavity mode. And because this is a bad cavity, this kappa, this rate of leakage, is very, very high. Now, because this rate of leakage is very high, in like what we can do is something called an adiabatic elimination. What that means is that we can essentially neglect this any time derivative. So for time which is larger than this kappa inverse, we can essentially neglect any time derivative, and we can equate these cavity modes with this collective spin operators. And using this relation, we can now rewrite the master equation in terms of only the atomic operators. But now, instead of a cavity decay, we now have a collective decay. So this is a Lindblad in terms of this collective spin operator. So this is essentially the master equation corresponding to the so-called atomic clock. Again, I will explain. So with this master equation, one can write down the mean field equations. So these are the mean field equations. Here we have rescaled the spins so that they are of the order of 1. And of course, to set the time scale, we have also equated this particular n gamma c to be equal to 1. And if you neglect the pumping, essentially this is a Landau-Lifshitz equation. And so again, this is, we are setting the unit of energy by setting n gamma c is equal to 1. We can go to the rotating frame so that this omega goes away. And if this omega goes away, then immediately you can see the phase diagram is essentially going to be one-dimensional, which is like, given by this parameter W. And what we see is that this expectation value of the cavity mode, which is proportional to the S minus, which I explained before, this will be non-zero, or in other words, you will have macroscopic population of cavity mode when W is less than 1, whereas when W is more than 1, this is equal to 0.
So Aniket, question here.
Yes,
So
please.
in the Landau-Lifshitz equation, you don't have any decay term, is it? This is the Landau-Lifshitz Gilbert equation, right? And it doesn't have a decay term, like a friction term?
No.
I see. So there is nothing which decays. There's a nonlinear. The last term is a nonlinear term.
Yeah, this is one of those, like when you have a magnetic moment. This is one of those, this is an unrelated equation. So these coincidences, these are incidental. It's not like we were trying to derive a Landau-Lifshitz equation. What we see is that if we, if we set this W to be equal to 0, then we can cast it in this particular form.
Mm-hmm. Yeah. Okay, so usually the domain wall motion in materials follow this.
Right. So
you see a similarity here. That's what you're saying.
It's just like the equation, it's similarity at the level of equations, but physics is completely different. Yeah.
Mm-hmm. Okay, go ahead.
Okay. So very good. Now, so essentially when you have macroscopic population of the cavity mode, you have super radiance, and one can show that the intensity is proportional to n square. And using this, one can build an ultra-stable sub-millihertz line with optical laser of high quality factor. And because the intensity is so high, you don't have to do an additional interference measurement to measure the frequencies. And in a sense, you can measure the frequencies very accurately. And this leads to accurate time measurement. And as a result, you call this whole setup as atomic clock. So this was all about atomic clocks. Now, let me pose this question. Can atomic clocks synchronize? So to address this question, one needs to devise a particular experimental setup where you have now two such atomic ensembles spatially separated, and they are also detuned from each other. You can use some magnetic field to detune them, or you can use some two different lasers to detune them. And this detuning is given by this delta. And you again have the pumping rate W. And like all the other things were just as you had for the atomic clock, in the sense that you have a coupling between the two-level atoms and the cavity modes, et cetera, et cetera. Now, this particular experimental setup was actually considered by Xu et al. And this is the phase diagram that they obtained in terms of W and delta. So they obtained something called a synchronized phase, unsynchronized phase, and no quantum correlation. Now, let me give you some salient points from their paper. First of all, they said that in this red region, there is no quantum correlation because quantum noise due to pumping destroys the coherences. We agree with this conclusion. Then they say that this region, the phase, is unsynchronized because coherent coupling is not sufficient to overcome the relative precision that arises from detuning. We do not, like our mean field results do not agree with this conclusion. Then they say that these two phases, synchronized and unsynchronized, they are on either side of the critical region are abruptly separated. We agree with this. But then they say that this separation is like a second order quantum. So this phase transition is like a second order quantum phase transition. We again disagree here. So now, right at the get-go, let me summarize our results and show you our phase diagram. So the main point of our result is that we show appearance, then disappearance via quasi-periodic root to chaos, and again, restoration of synchronization, where again, here the clocks, these clocks, again, as you saw in the atomic clock that I discussed earlier, the clocks are described by these collective spin operators, and W is the repump rate and delta is the detuning. So this phase number one is the normal phase where there is no radiation. Phase number two is the monochromatic superradiance. Now, in this phase number three, we have something called amplitude modulated superradiance. So in the amplitude modulated superradiance, one has symmetric limit cycles in this green region. One can also have symmetry broken limit cycle in this yellow region. And if you zoom in, you can have quasi-periodicity in this blue regions, chaos in this orange regions, and in the red points here, you have synchronized chaos. And hopefully I will explain at least one feature of this phase diagram. So just to compare, this was their phase diagram. But they say that no quantum correlation, synchronized and unsynchronized. So essentially what they obtained, Xu et al., they essentially obtained the steady state solutions of just the one spin equation, where this normal phase is no quantum correlation, and by synchronization, they mean monochromatic superradiance. That is all. So to answer the earlier posed question, can atomic clocks synchronize? We give an emphatic yes. And let me define what I mean by synchronization here. So what I mean by synchronization is that the spins corresponding to the two separate ensembles follow each other, meaning this A and B. So remember this A and B, these are the two different atomic clocks of the two different ensembles, which are now described by these collective spin operators. And this collective spin operators have this particular relation. So this is what I mean by two, like they follow each other. And if you now recall the antiphase synchronization between the two clocks, so in Christian Huygens experiment, so the pendulums are at opposite apexes at the same time. So here, essentially what we are doing is that we are replacing the pendulums with spins, and we are replacing the median, that's the dashed line, with the XZ plane. Now, if this definition seems quite vague, let me explain this. So one can write down the mean field, one can write down the master equation corresponding to this particular experimental setup, and one can derive the mean field equations as well. Just to compare, this is the one clock mean field equation. So
Aniket,
now,
just a small clarification. So the synchronization looks like a parity transformation. Is that correct?
Very good.
It's
yes. Yes.
It very much looks like that. Okay, fine.
Yeah,
fine.
It is.
Okay, thank you. So maybe
I'm just going to explain how this is, but in crux,
perfect.
you have it. Yes.
Okay, thank you. Yeah, bye.
Yes.
Go ahead.
Thanks for the clarification. Thank you. So very good. Now here you have this tau. This is like A and B. So these are the two separate ensembles, and this L is the SA plus SB. So this is now two coupled Landau-Lifshitz equation with pumping. And first of all, this has a symmetry. This has a axial symmetry, like so. And using the axial symmetry, one can go to the rotating frame, in which you can subtract the mean frequency, which is this omega A plus omega B by 2. And this then produces these 6 equations. So 3 corresponding to SA, but they are coupled via this L terms. And again, 3 corresponding to SB. Now, if you do this transformation, which was very nicely pointed out by Professor Das, that this is like the parity transformation, what essentially happens is that A spin goes to B spin, but the equations remain unchanged. So this is a symmetry of these 6 equations. So this is the particular Z2. So like this is the Z2 symmetry, which is similar to particle hole or parity transformation. So if I go back to my earlier definition of synchronization, so first of all, the phases might spontaneously break one of these symmetries or both of them, meaning this axial and the Z2 symmetry. And synchronized phase is something that has this Z2 symmetry in our definition. So for the rest of the talk, I'm going to focus on this one particular very sort of exotic phase called chaotic synchronization. And I'm going to talk about the origin, the experimental signature, experimental feasibility, and possible applications of this particular phase. So first of all, note that the chaotic phases, meaning both the orange points and the red points, they have maximum Lyapunov exponent, which is positive. So this we have calculated. Now, normal chaotic trajectories, which are the asymptotic solutions of these 6 mean field equations, they do not have this Z2 symmetry, and they occupy an extended region in the 60 phase space. The Z2 symmetry is restored for the chaotic trajectories at this red part of this phase diagram. Now, although the overall behavior is chaotic, the motion of one spin exactly follows the other, which again, recall the definition. To determine the origin, we have to now study the mean field equations, but now we have to restrict them on the Z2 symmetric synchronization submanifold. So the full manifold was 6-dimensional, but now using the constraint relations, those were these 3 constraint relations, we now have to go to the submanifold, which is now 3-dimensional. So that results in these equations. So recall, the original atomic clock equation was like single atomic clock equation was also 3-dimensional, but this is not like that. first of all, because note the appearance of these delta terms. These were not there in the atomic clock. So it still has a two-dimensional phase diagram, but now it has fewer phases. It now has fixed points, limit cycles, and chaos. By the way, the chaos in the Z2 symmetric submanifold is going to be chaotic synchronization in the full manifold. So synchronized from this phase diagram, it's apparent that synchronized chaos essentially originates directly from Z2 symmetric limit cycles. And we see that right after they originate, the synchronized chaotic trajectories, the trajectories spend long time close to the Z2 symmetric limit cycles. Now this blue line, if you can see, this is the limit cycle, and the dashed orange line is chaos. And you can see that they are almost the same, but not quite. And we have calculated the maximum Lyapunov exponents, and you can see that the chaos corresponds to more than 0, whereas the limit cycle is 0.
Aniket, sorry, one more question. I see the numbers here. So is it like in units of H cut, the S values, or this 0.5 is in units of really fundamental H cut, or it's something else? It's,
No. So
it's arbitrary scale. I should not try to.
So these are rates, right? These delta and W, these are rates.
Oh, these are, I see, okay.
Because this is, delta was like, delta was detuning. So this is energy, which is again, like rate.
I see. On the y-axis, you mean it's not the spin size? I mean, maybe I'm confusing.
No. Sorry. So this is the spin size.
Yeah, I see that it's like bounded by 0.5. So these are like spin halves. I'm just curious. Is it
yes. Because
these are like spin halves, I see.
Also rescaled them. Right?
Oh, they have rescaled. I'll tell you why I'm asking this question. I remember there was a PRL few years back where they said the minimum size of the spin which you need to synchronize 2 spins is probably spin 1. And there was they said that you cannot synchronize 2 spin halves. Maybe with an environment you can, but if you individually look at them, there was this PRL paper which came up with this idea that there is a minimum size to synchronization.
That's very good. Yes.
And I'm just curious, this 0.5. So that's the question. Just maybe you know
the valid point. So remember, we are not talking about synchronizing 2 individual spins. So we are talking about synchronizing 2 classical spin operators, and these classical spin operators, they correspond to an ensemble of 2-level atoms. So
these are like emergent. They are not like fundamental spins. Yeah.
No.
Yeah.
So in fact, I agree wholeheartedly with. I think this was from maybe from Rosario Fazio's group. That was
probably. I mean, I just don't remember now, but I remember seeing this. That's why I thought.
We agree wholeheartedly that if you have individual spins, then then it's hard to synchronize them, especially if you have environments, because then they will just decay away.
So this setup is also important for this thing to happen, basically.
Right. You definitely need an ensemble. You definitely need ensembles of 2-level atoms. And the size is essentially because I think the size should be the maximum. It should go up to 1 because we have rescaled them by n by 2.
I understand. Okay. I saw this 0.5 and I got curious. I saw the 0.5 on the axis and just got curious.
That's a valid point, and it's a source of major confusion in the field. Yes, but just to clarify, we are talking about synchronizing 2 ensemble of spins, not 2 individual spins.
Yeah.
And the spin operators that we have here, they are like emergent classical spin operators.
Yes. Okay. Thank you. Yeah. Okay.
Thank you. So of course. This particular scenario of chaos is known, and this is essentially what is tangent bifurcation intermittency. So another point is that right after manifestation, the synchronized chaos is not stable in the 6-dimensional phase space. And you can just compare the 2 phase diagrams side by side, and I have plotted this dot dashed line here, and you can see that if you there these points are essentially quasi-periodic, or chaotic. So for example, this particular point, W is equal to 0.055, delta is equal to 0.106. By the way, they are in the units of n gamma c, where n is the number of atoms and gamma c is this collective decay rate. So we set that to 1. And so at that particular point, we see quasi-periodicity for non-Z2 symmetric initial conditions. So if you choose any random initial condition, you will see quasi-periodicity. But if you choose a Z2 symmetric initial condition, you will see chaos, or in other words, you will see synchronized chaos. So one can, in fact, study this a little bit further. And what you do is that you set the W to be constant. And then if you decrease delta, this chaos will become fully synchronized via on-off intermittency, which is again expected. And here you see that, this SZA minus SZB. So for fully synchronized scenario, this should be 0. Now you see that this flares up and then again goes back, flares up again. So just look at this delta value. So this is for delta 0.08021. We decrease it further, you see that there are less flaring up now, and decrease it to this particular value, there is almost no flare up at all. So essentially the frequency and outbursts of this chaotic outburst, essentially they decrease as we decrease delta. And the same behavior is observed for this S-spark, where this S-spark is square root of Sx square plus Sy square. Just to be sure, we have also calculated the conditional Lyapunov exponent, which is the maximum Lyapunov exponent for the direction, which is transverse to the synchronized manifold. And we found this to be negative for the synchronized chaotic trajectories. Remember, the maximum Lyapunov exponent is positive, but the maximum conditional Lyapunov exponent is negative. So for the experimental signature, what we propose is that study the autocorrelation functions. And these autocorrelation functions can be measured using a Michelson interferometric experimental setup. And if you do the Fourier transform, so in our mean field picture, this Fourier transform of this electric field is essentially proportional to this L minus. And here we plot this L minus. So first of all, for the chaotic synchronized trajectories at this particular value of delta and W, you see a continuum, which is expected. But one important thing is that you see reflection symmetry about the origin, which you explain by noting that Ly is equal to 0. And this is because of the synchronization manifold, because of the relation between SYA and SYB. Now, if you zoom in close to the 0 frequency, you see that there is no peak at the origin. So this is a magnified picture. And this is essentially a leftover from the Z2 symmetric limit cycle. Remember that this chaos is essentially, this comes from the Z2 symmetric limit cycle. And in the Z2 symmetric limit cycle, it only has odd harmonics. So that's why you have no peak at 0. Just to compare, I plot in the same scale I'm plotting here a normal chaotic trajectory. You see that there is a huge peak at 0. Okay. So for experimental feasibility, typical experimental setup, the spontaneous emission can be pushed up to 100 seconds, and the inhomogeneous lifetime T2 can be as large as 1 second. So, like the rates corresponding to these two processes are very, very small. So one can essentially neglect them because the chaotic synchronization reaches the steady state. So here I'm plotting SZA minus SZB. So you see that it reaches the steady state in about 70 to 140 milliseconds. So essentially you can neglect these two effects. And also in current experiment, one can see super radiant emission for 120 milliseconds. So we believe this is enough to observe chaotic synchronization. And of course, the unit of time is 1 over n gamma c, remember. So We neglect spontaneous emission in homogeneous lifetime. And also, if there is loss of atoms from the traps with different rates leading to atom number imbalance, we show that, like, if this was completely synchronized, meaning if the number of atoms in both these traps are exactly equal, then this is just one line passing through the origin with slope 45 degree. But now it's somewhat modified, but the modification is just, it's a perturbative effect. So it breaks the Z2 symmetry, but only perturbatively. This can be, so that was about the experimental feasibility. Now I come to the application. So the application of chaotic synchronization is something called optical chaos communication. So the way you do it is that you add message to one of these chaotic temporal patterns from one ensemble. But of course, the amplitude of the message must be small so that it can be treated as a perturbation over the synchronization. And then you subtract the synchronized output from the transmitted signal, retrieving the message. And here I'm showing the protocol from the book by Uchida. So what you do is you add the message to the chaotic carrier. This is the signal, you receive it, and you now subtract the original chaotic carrier and decode the message. So the main purpose here is not to hide the meaning of the message, as is done in cryptography, but what we are doing is we are hiding the existence of the message itself. So this is called steganography. So this is a new way of transmitting secret messages. Okay, so just to conclude, we showed that coupled atomic clocks inside a bad cavity have a rich non-equilibrium phase diagram. For a significant part of the phase diagram, the spins remain synchronized, where we use the term synchronization in a general sense that includes monochromatic superradiance. Synchronization is destroyed when chaos sets in through quasi-periodicity. In finite part of the subregion of the phase diagram, even the chaos is synchronized, that is, although the dynamics of spins corresponding to individual clocks are chaotic, one spin exactly follows the other. And it might be possible to utilize this particular synchronized chaos to implement novel cryptography protocols. Future direction. Okay, we considered a really bad cavity where Markovian picture is valid. One can consider not so bad cavity where adiabatic elimination is not possible. In that case, you will have a non-Markovian master equation. What will happen? We don't really know. What will happen if you consider n much larger than 1 inside one cavity? We again don't know. We consider just a single mode cavity, meaning the ensembles were coupled to one cavity mode. So we don't know what will happen if you couple to multi-mode cavity. By the way, the oscillations that we talked about, these are something similar to boundary time crystals that was already observed by, or that was proposed by the group of Rosario Fazio. So studies in that same direction can be pursued. Now another question is, we just studied the mean field diagram. What happens if we study the full quantum system? Do we have dark quantum states that we cannot access by looking at the mean field dynamics? We don't know the answer to this question. Now this coexistence of chaos and other regular behaviors is interesting from a mathematical point of view, like from the point of view of nonlinear dynamics. Question is, can this concept of mixed phase diagram in Hamiltonian system be extended here? Remember, our system is not Hamiltonian. Another interesting, tricky mathematical question is that we don't know the mechanism of quasi-periodic route to chaos, meaning we see quasi-periodicity and then we see chaos, but we don't know exactly how it happens. Is it a torus destruction? We don't know. Is it possible to obtain obtain chaotic attractor with reversible core? For instance, you can check out this nice review article by Gonchenko et al. We don't really know, but this can be interesting mathematical questions. So these are the future directions. And So these are the 3 papers that describe the full extent of the phase diagrams. And this work was done in collaboration with my PhD advisor, Emil Yusbarshian from Rutgers University and Boris Altshuler from Columbia University. And these are the phase diagrams. Thank you very much for your attention.
Thanks for the wonderful talk. So now the floor is open for questions.
Aniket, I have a couple of questions. Yeah.
Yes.
See, in the super-radiant phase, so that is basically, so light is coming out like a dipole emission from dipole emission, or how do you explain? I mean, you are not dealing with anything quantum mechanical.
No. So I'm just dealing I'm talking about having, for example, like if I. So it's something like superfluidity or something like that.
Okay.
So you have macroscopic population of this cavity mode. So what I mean is that.
Okay. So that is like, somewhat like laser kind of thing. Huh?
Yes, precisely. That's why this statement that you can build a optical laser using this superradiance.
Okay. Now the other thing is that this chaos. I mean, you are. I think you mentioned about that you have studied the classical regime where you are seeing chaos and these kind of things. Now, if you go to quantum regime, maybe it will be possible to see this transition between quantum to classical, because because quantum chaos has a very different kind of connotation.
Yeah. Yes. So you mean like in the how do you propose like we look at the level?
Or maybe more through dynamics. See, level statistics.
Level spacing we cannot observe, right? Because this is not a.
So you should look for some dynamical signature.
There is a paper, I think, by Carol, and this is a group from Poland, and Sergei Denisov, I think, is the first author. So who study the level spacing related to these link blood operators.
Yes.
So so we don't. I mean that is a very interesting suggestion. And a number of things can happen. So this is just like we just scratched the surface. We just scratched the surface in terms of the mean field equations.
Yes.
And we have studied the classical equations to death. But of course, when it comes to the full quantum picture, we can do So you mean something like the Otto, meaning?
Yeah.
Right. Yeah. Using something maybe like Keldysh or something. Yeah. I mean, there are many a number of interesting possibilities. It's just after I did this work, it already took the better part of my PhD, and result at the very end of my PhD, I could write this 3 papers, and then essentially I haven't gone back to this problem since. But as you say, I mean, there can be many interesting possibilities.
Okay, Aniket, see you.
Yeah, thank you.
Okay, so are there any